after this. All right. The next example, I give you two uniform distributions, and you need to find the distribution of the sum of these two uniform distributions. Let x be uniform 0, 1, and y be uniform 0, 1, be independent random variables. Then z equals, and here I'm giving you what the distribution of z looks like. Then z has triangular density given as follows. First of all, why do I call this a triangular density? But graph this and tell me what that looks like.
That looks like a triangle.
So graph that. Go ahead.
I did it in my head.
Yeah, right. Well, you have a sheet of paper in front of you, so go ahead. Put that down on paper. So the reason why I call that triangular distribution triangular density. So what does the graph of this density function look like? So 0 when z is less than 0, it's 0 when, so these are the important values. 1, 2. So it's z, which is just a linear function in the interval 0 to 1. So it's this in the interval 0 to 1. We call this 1. It's just up to there, right? Now, 2 minus z is also a linear function with the slope going down, right? Okay. So at the point, so let's just mark 2 points. What's its value at z equals 2? It's 0. What's its value at z equals 1? It's 1. So your density function curve is 0 everywhere, and then it increases, and then it drops up, and the shape is triangular. So basically it says the probability that the sum takes some values around 1, that probability is very high. Right? The probability that it takes small values is very low, the probability it takes very large values is very high. And you can see that because probability for z to take small values means both x and y have to take small values. For z to take large values, it means both x and y have to take large values. But for z to take values in the range 1, I mean, x can take values all the way from it can take small values, but y can take large values. X can take large values and y takes small values, or x and y can both take values around 1/2. So there are a lot more options to combine to give values in this region. So it sort of makes sense, even intuitively, to see that there's a higher probability of taking values out here and lesser probability of getting the sum to be very small values. All right. So what's the formula that we use for this? Well, first of all, let's write down the density function for each of these. Density function for x, density function for y. Density function for x is just 1 over the length of the interval, which is 1. this also. And what does your density function for y look like? So if what I've stated is true, it means that uniform distribution is not self-reproducing. So if I take two independent uniform distributions, I add them, I don't get uniform anymore. Okay, so if I want the density function of the sum, what's my formula for the density function of z? Formula out here. It's just this integral from negative plus infinity y z. How many of you have come across these things called convolutions before? So an integral of this form, you get a function of z by integrating f of some function of x and some function of z minus x. It's called convolution. And whenever you have to find the density function of a sum, you use this convolution formula. Okay, so let's see what we have to integrate over. Now we know that this is we need to integrate over the region. This product will be non-negative when both of these are not. Will be non-zero if both of these are not zero, right? So this is not zero when x is between 0 and 1. This is not zero when when y is between when z minus x is between 0 and 1. The integrand to be non-zero need both these things to hold. Need this to be between 0 and 1 and this to be between 0 and 1. So whatever number I plug in for this and whatever number I plug in for this has to be between 0 and 1. All right. So clearly if, okay, so we'll have to do this in several cases. For z, first of all, we know that z cannot take values less than 0, cannot take values more than 2 because I'm summing up to 0 and 1. So if z is between 0 and 1, what do I know? This has to hold. If z is between 0 and 1, then that means your, actually let's rewrite this. So we basically need inequalities in terms of x, right? Because we want to know what to integrate over. So this is 0 is less than z minus x, which means x is less than z. And z minus x is less than 1, which means x is greater than z minus 1. So z minus 1. So that's how I should write it. So solve this inequality for x, you get x is greater than z minus 1. Solve this inequality for x, you get x is less than z. So in terms of x, x is between z minus 1 and z. All right. If z is between 0 and 1, this is negative. But x has to be greater than 0. So for z in this interval, fz of z, you need to integrate x going, don't look at this lower limit, look at this one. And z is less than 1, so you cannot integrate up to that. Because if you integrate above z going to 1, this part would be 0. This thing would be 0. So you go from 0 to z. All right. So integrate from 0 to z. What is your function? 1 and 1 dx. Find what that is for z between 1 and 2. So you tell me what I need to integrate out here. Where this will be both. this when I integrate this, I can see.
I'm sorry, what are you integrating? I can't see it. It's from 0 to z.
Yeah.
What is that?
So what is fx
There's
of
a
x?
glare on the board.
Oh,
I
yeah.
can't read it.
So let's think about it. I have to integrate between 0 to z, this function times this function. What is this function? It's going to be 1. Because I'm basically trying to find the region where this is 1.
So
right?
it's just 1
so
times
1 times 1. Yeah.
Okay, I see.
Right. So again, basically, I want to know over what interval can I say it's 1 times 1 differences. If it's 1 times 0, then it becomes 0. So I'm going to only look at the region where this is between 0 and 1, this is between 0 and 1, so that I know I'm just multiplying 1 times 1. All right, so what should the lower limit be? What should the upper limit be? So remember, both of these have to be satisfied simultaneously. Okay? Only then will I get 1 times 1. Otherwise, I will get 0.
Would the lower limit be z minus 1?
Z minus 1 because because z minus 1 is going to be greater than 0, right? So this would be less than that. So you want from z minus 1 exactly. Z is now more than 1, but you cannot go beyond 1.
So 2, 1.
To 1, exactly.
Okay.
And when you integrate this, x between z minus 1 and 1, you get 1 minus z minus 1, 1 minus z plus 1. So this is something that we've done before too. You've got to be careful about your limits of integration when, so at this point you know negative infinity to plus infinity, but you only want to consider limits of integration where these things are non-zero. And here it's non-zero when you integrate between 0 and z, non-zero when you integrate between z minus 1 and 1.
Explain that second on the integral of the bounds. The bounds on the second one.
Z minus 1 to 1?
Yeah.
Okay. So I need to integrate over all values of x where both of these things hold, right? Now I'm looking at the case where z is greater than 1. Okay? That means I need both this and this to hold. So x has to be greater than 0, but x also has to be greater than z minus 1. So that means I need to take x greater than z minus 1. Because if I take x starting from 0, then it could be less than z minus 1, right? And in that case, this would be violated. My x has to be greater than z minus 1 always, right? When z is negative, if I take x greater than 0, it's automatically greater than z minus 1. But in this case, if z is greater than 1, then to ensure that both of these hold, I need to take x greater than z minus 1.
Well, it can be equal to 1, so one can be something to 0.
Wait, no, here can be
For
equal
z
to
less than or equal to 1, what's the lower bound for?
z less than or equal to 1. Oh, the upper limit?
Z is between 1 and 2.
Right, yeah. I'm integrating over x. So what are the possible values that x can take? Well, what should I integrate over? X should satisfy both these conditions, this and this. So what's the lower end point? So x has to be greater than 0 and it has to be greater than z minus 1. So it has to be greater than z minus 1 in this case. If I start integrating from 0, what happens? When I integrate from 0 to z minus 1, I actually get 0 here. So I can't integrate from 0 to z minus 1. I need to integrate only from z minus 1 onwards. So, but think about this. You just want to find your limits of the right limits of integration so that when you plug these things in, you get 1. So if you plug in any number that's less than z minus 1, one of your integrands will be 0. Okay, so let's go over this again. So we have this formula, right? Now when we want to evaluate that formula, we know that either the integrand can be 1 or it can be 0, right? Because each of these can either take the values 1 or 0. I want to ignore the places where there's 0. So only integrate over the region where it's 1, right? So when will this be 1? This will be 1 when x is between 0 and 1, okay? So I definitely want x to be between 0 and 1. And when will this be 1? When z minus x is between 0 and 1. That is when z minus x is between 0 and 1. So that means I need x to be between 0 and 1 and between z minus 1 and z. Okay? From this, just solve for what inequality x satisfies. Okay? Has to be between z minus 1 and z. So if x has to satisfy both, in each case, let's see when does it satisfy both. If z is between 0 and 1, I can start integrating from 0 because if I integrate from 0, automatically x is greater than 0 and greater than z minus 1. So if I integrate from z minus 1, then there's a problem because x is not greater than 0 in this case. So if I want both to be true, my lower limit has to be 0 here. My upper limit has to be z. I cannot integrate all the way to 1 because if I integrate all the way to 1, this would be violated. It would be more than z. Okay, so I stop integrating at z. Now, in this case, if z is between 1 and 2, again, I need to integrate over all values of x where both of these are satisfied. If I started integrating from 0, that means z minus 1 is negative. Z minus 1 here, sorry, is positive. So if I integrate from 0, x might be less than z minus 1, right? So I want to avoid that. So start with z minus 1. And then, should I go all the way up to z? No, because z is above 1, and I need to make sure this is satisfied. So I only integrate up to 1. Okay? So keep in mind, both these conditions have to hold. So obviously, when you have to plug in what your integrand is, you want to make sure that your integrand is not 0. So check when is this not 0, when is this not 0, for what values of x, for what values of z minus x. So you'll always, whenever you use this convolution formula, you've come up with a condition like this. Okay? This has to be satisfied for x, this has to be satisfied for z minus x. All right, let's do another problem with continuous distributions.
Is that convolution formula general or specific to this problem?
This formula is general.
Oh.
I mean, yeah, this formula is general, of course.
Okay.
But then, I mean, here we're going to apply it. So plugging in 1, it's particular only to uniform distribution.
Oh, okay.
Let's do homework problem. Okay. The next thing I'm going to state is a theorem, and it's in the textbook, so I'd like you to just look at the proof of the textbook. So let's take sums of normal random variables. Write down the general formulas here. Very important. So these formulas were derived only for independent random variables. Probability mass function is sum over all possible x's, x, py of c minus x. Density function C all right, the next thing I'm just going to state as a theorem, sums of independent take this as a theorem. The proof is in the book, and I'll just let you read it. I mean, doing it is kind of working. I mean, actually doing that integration is kind of tedious. If xi and independent variable with xi distributed. So each of these xi's are distributed as normal with mean mu I and variance sigma I. So xi is distributed with, and all the xi's are independent. So independent, and each of them is normal. The mean for xi is mu I, the variance for xi is sigma I squared. Then if I look at the sum of these n independent identically distributed normal random variables, their sum is also normal with the means and the variances is added. And for the proof, so look at read page 256 to 257 in the textbook. That's covered up there. So it's going to take too much time to work this out in class. So, but all you need to know is the statement. So normal is another self-reproducing random variable where if you have the sums of independent normally distributed random variables, their sum is also normal. Find density function of Z, and Z is the sum of x plus y, and joint density of the two is Now, what's the big difference between this and everything else that I've done so far today?
You have a function of x and y?
Yes, so that means, are they independent?
No.
No. They could have been independent. I mean, like you could have checked, found their marginal probability density functions and checked that they're actually independent. What makes you so sure they're not independent?
Y is not greater than x.
Exactly, yeah. So I said if the domain over which this is defined is not rectangular, which is something like this, they're clearly linked to each other. Because this says that you cannot have y less than x. That's clearly somewhat dependent. So in this problem, x and y are not independent. So So you cannot use those formulas. Use convolution formulas. By convolution formulas, I mean formulas of this form. Okay, so then if you have a problem, these are clearly continuous random variables. To find the density function, so this is something that you should be able to guess by now. I'm looking, so when we did functions of one random variable and asked you to find the density function, you realize you couldn't find the density function directly, you first find the distribution function. Same thing here. It's a function of two random variables, but it's the same idea. If I have a function of two random variables, then again, you can't find the density function of z directly, you first find the distribution function. All right, so let's first find the distribution function of z, and then we will differentiate and get the density function. So how does this go? Fz, let's say f little z, is just the probability that x plus y is less than or equal to little z. So these are two random variables. This is a number. This is not a random variable. This is a variable. You can say it's not random. All right. So I'm interested in the probability involving two random variables. I have the joint density function. I just integrate the joint density function over this region. So you just have to integrate this joint density function over the region x plus y less than or equal to z. So now this question of you have to figure out the region over which you're going to integrate. First of all, where is this joint density function non-zero? It's non-zero in the region when, okay, first of all, x can only take values between 0 and 1. That's a good thing to know. And what else do we know? That x has to be less than or equal to y. Or, so let's draw the line x equals y. And we're interested in the region y greater than x. So this is the region where the density function is non-zero. So your y is greater than x. All right. You are interested in integrating over the region x plus y less than or equal to z. The boundary of that region is x plus y equals z. So let's so z is some number, okay, and we want x plus y equals z, or you can write it as y equals negative x plus z. X is 0, y is c. Okay, and we are interested in the region x plus y, okay, less than equal to z. X plus y less than equal to z. We are interested in the region y less than equal to negative x plus z. All right. Negative x. Oh, there's one more thing we should have talked about first. What are the possible values z can take? So x and y both take values between 0 and 1. So z takes values between 0 and 2.
Mm-hmm.
Yeah. So okay, when z equals 0, y equals negative x is a line that goes like this. As z increases, it's a line that, you know, the z is the intercept. And z equals 1 is there, z equals something higher. That's okay. All right. Z equals. All right. Our question is, does you see that when z is 1, then when x is 0, then y equals 1. So when z is 1, you have a line like this, right? And when z is greater than 1, you will have a line that would intersect this part here, right? And when z is less than 1, you have a region like this. So clearly, when z is 1, your limits of integration are going to change. So this is when z is less than 1, this is when z equals 1. And this is the line you get when z is greater than 1. All right, so let's consider different cases. So case when z. So in the case when z is between 0 and 1, say this is a typical line. So it starts from here. Let's draw this separately. See, right? And here's our line. We are interested in the region y less than or equal to negative x plus c. So this is our region of interest, right? So this is our line y equals negative x plus c. And we're interested in y less than that, but y has to be greater than x. So this is our region. So you would integrate from here to here, and x going from here to whatever this point is here, and y going from this line to this line. So first of all, you need to find the point of intersection of these two graphs. So what's the point of intersection of y equals x and y equals negative x plus c? So it's x equals negative x plus c, or 2x equals c, or 2 equals 0 over 2. So this is the point 0 over 2. All right, so our probability fz of z is going to be the integral x going from 0 to a z over 2, your y going from the line x to the line minus x plus z. And your density function at that point is 2x y dy. So remember, what we're basically trying to keep in mind is we want a region where and the region where with y less than or equal to negative x. So we want our y's to satisfy both of these, right? Between 0 and 1. And okay, so that puts restrictions on the possible values that this can take. All right, so we'll integrate that. Tell me what you get. Let's look at the next case. So I'll leave the integration to you guys. Let's move on to the next case. Case 2. If z is between, what does this look like? So this is z is 1. So then so when z is greater than 1, this is your line y equals negative x plus z. So line y plus x. Yeah, just x. And y has to be less than or equal to. So this is your region of interest. Yeah. Okay. So your region of interest here is y is greater than x, so it's above this line, but it's less than this, okay? And it doesn't exceed y equals 1. So these are your conditions. So this is your region of integration. All right. So for this region of integration, it might be best to go from. I'll have to split it into two sums, I think, right? Mm-hmm. Yeah. Okay, so let's split it into. So where does it intersect the line y equals 1? So C. X plus C, X equals Z minus 1. So, okay. So X goes from Z, that's Z minus 1. Is that right? Yeah, okay. So as X goes from 0 to Z minus 1, you're going to integrate Y from X to 1. And as X goes from Z minus 1 to, what's the point of intersection here? Z over 2, right? Z over 2. As X goes from Z minus 1 to Z over 2, you integrate from X to minus X plus 2. So now, Fz of C equals integral X going from 0 to Z minus 1, and you integrate your Y going from X to 1, okay, and put in your density function here, dx, plus as X goes from Z minus 1 to Z over 2, your Y goes from X to minus X plus Z. All right, so this problem is a lot more complicated than anything I'd give you on the exam, but I mean, you have to realize that these are the problems you face. It's basically a calculus problem that's making it really difficult, but well, you need to know. This is why you need to know calculus. All right, so these are like the only difficulties. You need to make sure that for your integrand to be non-negative, you need to take into account the region over which is non-negative and the region over which you're integrating, which is the region x plus y less than equal to 0. So once you have that, I think graphically is the best way to do it, because you can see, okay, exactly what region you should integrate, so you know what points of intersection to have. But if you're just thinking in terms of inequalities, what inequalities are you looking at? These are the two inequalities that have to be satisfied always. You see that when z is between 0 and 1, then you have minus x plus z, okay? But, or rather say if z is greater than 1, okay, then minus x plus z is going to be something positive, right? So, so this makes sense. But if z and it's going to be something positive, anyway, I find it easy to work with the graphs. Okay, so these are like some of the few things you have to think about when you're actually solving these problems. You think about the calculus part of it. All right, so with this, and I mentioned that we would look at functions of two random variables. This is the method we use. So this was a very simple function. It was just x plus y. I could ask you, find the distribution function, find the density function. Oh, we're not done. Yeah, that's the distribution function. So once you get your answer, differentiate that. So I'll leave that to you guys. So I could ask you, find the density function of x squared plus y squared. Same idea. You start with the distribution function, right? X squared plus y squared less than equal to z. Integrate over this region where x squared plus y squared less than equal to z. X squared plus y squared less than equal to z, that's a circle, right? With the radius z, z squared z. And then you can figure it out from calculus.
So there would be two, this would be case one after we integrate and we differentiate
Yeah,
that.
so you'd have the density function only for the region 0 to 1.
So we would have two different density functions, correct?
Well, not two different, but piecewise different, yeah.
It would be a piecewise one.
Right.
Okay.
Yeah, so when 0 less than equal to z less than equal to 1, you'll have whatever answer you get from differentiating this.
Okay.
And then 1 less than equal to z less than equal to 2. Basically like how we had piecewise defined function and 0 elsewhere. So we already know it doesn't take any values outside of 0.
What's that second double integral?
Here?
Yeah.
Okay. So the outer integral is x going from z minus 1 to z over 2, and y goes from x to minus x plus z. Okay? So from x to this line is minus x plus z.
So it was z times x.
2 times x plus y here. This function. Yeah, just the joint density function like that. All right.
What do you differentiate with respect to?
You differentiate with respect to z, little z. So here too, you differentiate with respect to this little z here. All right, okay, so we start with section next. We start with conditional probability.
Are you gonna post that homework?